Hi and welcome to this video about writing a WinDbg extension. WinDbg is a debugger many of you are familiar with to one extent or another. And in fact, WinDbg is very extensible. You can have custom commands loaded into the debugger by building extension DLLs. In fact, many of the commands you use in WinDbg, like on a daily basis, if you're using WinDbg on a daily basis, are actually extension commands coming from extension DLLs, which are provided as part of the debugging for Windows package. But you could write your own DLLs to provide extra commands that might help you in debugging or other kinds of activities you do with the debugger. Okay, so in general, if you look at WinDbg commands, you have three types of commands. One type is called regular commands. And these are commands which are part of the debugger engine. They don't require anything external, they just use the actual debugger engine. It's part of the engine itself. And of course, they work on whatever you are debugging. If you're debugging a process, that's be the process. And if you're debugging a machine, that is a kernel type of debugging, then it's about the target that you're debugging. And then there are meta commands. Meta commands start with a dot and they represent various commands that affect the environment of debugging. For example, the .reload command will reload symbols if you've made any configuration changes. The .cls command will clear the screen, and so on. And obviously they're also part of the debugger engine. And then the third type of commands that we have are known as extension commands or bang commands. These are the ones starting with exclamation mark, and these are the ones provided by external DLLs or extension DLLs. And some of which, as I mentioned, are provided as part of the package. And in this video, we'll write a simple extension DLL to show how you might go about it. Because at the end of the day, you might be able to do everything that you need with the existing commands, but you typically want to make things happen faster, do less work, because debugging is really about trying to minimize the work you need to do. So in general, to write a WinDbg extension DLL, here's what you need to do. You need to create a normal DLL and export a bunch of functions. One function, as we'll see, is initialization function that you must export because WinDbg will call you, but then you expose commands as functions. So if you want to have a command called ABC, and of course it will always start with exclamation mark as a bang command in the actual debugger, then you can create a function called ABC and export it. Once you do that, the command will be automatically available once that extension DLL is loaded into the debugger. In order to load an extension, just use the .load command and provide a path to the extension DLL. If you want to unload the extension DLL, just go ahead and use the unload command. This is actually very useful while you're debugging the extension because you might want to test your extension as you're building it, and once it's loaded into the debugger, you can't rebuild it. You have to unload it first, otherwise the build will not succeed because the file is already open and taken, cannot be overridden. And then if you want to know more about WinDbg, if you're not familiar with WinDbg enough, I recommend, well, maybe it's maybe it's kind of silly, but I recommend the Mastering WinDbg course on Trainsec. Okay, we're done with the introductions. Let's go ahead and open Visual Studio and start working on our extension. So the first thing I'm going to do is to create a new project. I'm going to use the Windows Desktop Wizard template to get us an initial DLL. So let's call that types extension. Before I actually do that, I want to introduce the commands we're going to write. So I'm going to launch a debugger with admin privileges. Here's my WinDbgger here. And I'm going to start a local kernel debugging session because I want to create a command that has meaning in kernel debugging. In general, you can create a command that works in user mode or in kernel mode or both, depending on what you're trying to do. And of course, you can create any number of commands. So one thing that I'd like to do here in order to demonstrate how to create a WinDbg extension is to work with object types. And so you might know there's a command called object, and there's a directory in the object manager's namespace called object types. And if you try to look at that, you can see this directory in the object manager namespace has all these object types. So if I just click any one of them, I'll get information about the object, but that's not the point. I want to take the object and look at that as an object type. In order to do that, we can use the normal DT command with the object type data structure. This structure is not officially documented, but it is available in the symbols, so we can leverage that. So you can see that we have this object type. In this case, it's a session. It has an index, that's just an orderly index of various types. And then you can see there are total number of 2 objects right now, like 2 session objects that are available running on the system, exist on the system. There are 51 hex, that is 81 handles to these various session objects. And of course, we have the maximum number of objects, which is also 2, and the maximum number of handles. So any kind of object I choose, I'll see something very similar. Let's look at something perhaps a bit more familiar, like a process. So I'm going to use the same command, but pasting the address of the process object type. And you can see here that indeed the type name is process. The index in this case is 7. We have total number of objects, which is a lot, and total number of handles, which is even bigger. And we have the maximum or the peak one that is being tracked since Windows started. Now, one other way to see this information outside the debugger is by using one of my tools called Object Explorer. So here's Object Explorer, and one of its views shows these object types and also updates number of objects, handles, peak objects, peak handles every second or so. So what I want my command to do, the main command I would like to write, is to show this information, show some of these columns that we can see normally in the object type, like the index, the total number of object handles, the name, and so on, like things like that. And you might be wondering, if I have this Object Explorer tool, what's the point of writing a command? So you need to remember, of course, that WinDbg can also work in other scenarios, not necessarily on a live system, like when you're working with a dump file. In this case, no other tool can work for you because you're looking at some snapshot of memory and only commands in the debugger can do stuff. So I'd like to create a command that will go over all the type objects and provide like a nice table of all this information that we see here for every single type. So obviously, as I mentioned earlier, I could have just gone and continued doing that like manually. I can even perhaps write a script to do this automatically, but for this example, I'd like to write a WinDbg extension that will write a simple single command to provide all those details. And we use, of course, the debugger for testing purposes. So let's see what that might look like. So I'm going to go back here to Visual Studio. I'm going to call that typesxt, just as a name. Let's go with my YouTube code directory, and let's go ahead and create our DLL. So I'm going to select DLL here. We don't need that much. I'm going to stick with the defaults here just to get a little DLL main, which I'm not going to actually use, but it's just here. I'm going to leave it as is, and we're going to create a new source file to actually do the work. So let's create a source file called types.cpp, and this is where we're going to start doing the work. So first we need a bunch of includes, as you might imagine. We'll start with windows.h in order to get the standard definitions, and then we need the debugger engine header. This is where you get the debugger engine interfaces, constants, enumerations, and so on. The debugger engine, by the way, is documented. So if you go to the debugger and press F1 to launch the documentation, there's also documentation for the debugger engine. It's not great, but it is kind of doable. And so it's possible to definitely find information about debugger rated APIs. So we have various APIs, and there's even documentation, of course, how to create debugger extensions. You can see there's a link here, and I'm going to show you the basics of that. And there's the actual interfaces like iDebug client here, so we can look for that and then locate it. You can see that we have a debugger engine reference, and there's even an overview of how to work with the debugger engine, because it's possible to use it to build a debugger or many other kinds of tools that can use the power of the debugger engine. But we're going to focus on actual extension DLLs. That's it. It's relatively simple compared to writing a full-blown debugger or something like that. So anyway, we have the debugger engine interfaces. We might need them. Then there's an extension header file that's called WinDbg which provides some helper macros to make it slightly easier to write the implementation of the commands I'd like to implement. So I'm going to use that even though it's not technically necessary. And I'm going to use some smart pointers for COM because all the debugger interfaces are COM interfaces. I'm going to use ATL here, but we're not going to need that a lot. But still, I'm going to use ATL COM client header to get a CCOM pointer wrapper, that is the smart pointer for COM interfaces. And then we need to create our functions. So let's go ahead and start with the first one. The first one is called debug extension initialize. And this is the function that's being called by the debugger engine when our extension loads. And of course, there are some parameters here. There's a version and flags that we need to return here. You can see there are pointers too long. This std API just means hResult std call, which means we need to return an hResult, the COM hResult, to indicate success or failure when initializing the actual extension. So let's start by creating the debug client using the debug create function. This function is provided by the debugger engine. And so we're going to look for something like a debug client. So I'm going to go with UUID of iDebug client. This is the main interface, but of course we can ask for others. They're all implemented on the same object. And again, I'm going to use little void star here just to make things slightly easier without involving like various C++ reinterpret cast kind of things, to make it easier for those that don't feel comfortable enough with C++. So we're going to get a client interface here, and we're going to get an hResult back. If that doesn't work, then something is terribly wrong, and we're just going to return with that hResult because we can't move forward. What we want to do here, in order to get support for some nice macros that you get with WinDbg X here, we actually need to initialize a data structure that's called the WinDbg Extension APIs. And you can see there's 6432. Technically, we need a 64 version. I'm going to create the 64 version of this DLL, although we can, of course, then technically compile for 32 as well. I'm going to call that extension APIs, which is in fact the name that is expected to exist. And the first member has to be initialized with the size of the structure. So I'm going to do just that. And if we jump and see what's going on, you can see there's a bunch of callbacks here that we're going to initialize by a helper function in the debugger engine. And with that, we'll be able to get support for some nice macros and helpers to make our life slightly easier. It's not strictly necessary, but it's definitely makes things easier. So once we have that, we need to actually use a different interface, which is iDebug control, also implemented on the client. And what we need to do here is to call get WinDbg Extension API 64. That's the one that actually fills in that extension API structure. It just requires the structure to have the initialization for the first member, which is the size. And again, if there's some error, which shouldn't really happen, but let's just test it anyway, we'll just go ahead and do that. And finally, return a failure. And finally, we need to provide some information about the version of our extension. So there's a macro to do that. So we have a debug extension version, something like that. And we need to provide the major and minor version. So 1.0 seems good enough. There are no special flags we need to provide here. Let's just return SOK, and that is it. So in order to test this thing, let's just implement one function, one command, which is typically a help command. So it's very common to implement a help command. Let's go ahead and implement that. And all commands except have the same prototype in terms of functions. We just need to properly export them. And the command should expect iDebug client. That's the one coming from the debugger, of course, the debugger engine. So we can use that to do anything we want with the debugger as needed. And the second parameter is the actual argument. That is the arguments to the command. let's call that args. So in the case of the help command, there's nothing really we need to do except provide some output. And one of the macros that you get is dprintf. As part of these nice extensions, we can just say this is the object types help or something like that. And this is just like a normal printf with some extras, but of course that printf kind of thing is going to output to the debugger's command window and not some abstract console. So let's just say we have this command help, show this help, and we'll have just one command to implement in this video. It's going to be called object types. And so it's going to be something like display object types. And we can even do, or at least try to have some kind of filtering by name. So maybe we'll be able to write something like PRO and then find all the object types that have the name PRO. I'll leave that as an exercise for the interested reader or viewer. And then we'll just focus on the main implementation. So first let's build that, see if that builds successfully. So apparently it doesn't really build successfully, and that's because there's the thing is that the debugger assumes, the headers assume that I'm going to build a 32-bit DLL, and I have to define some constant here that's going to say that I'm actually interested in a 64-bit DLL. So let's try it again. So now it still doesn't build because the debug create function here doesn't seem to be implemented anywhere, and so we have to add the import library for the debugger engine. So it's going to be lib and dbgeng.lib, which is the one that contains the implementation. The actual DLL contains the implementation. This is the import library for debug create. If I do that, then it should now link successfully, and it does. Does that mean we can load the DLL? Well, we can try. So here's my debugger. Let's go with the load command. I need to find where exactly this thing is. So it's under YouTube code, and then we have types ext, and then x64 debug and types ext.dll. That should be the path. And apparently it managed to load something. Do we have something here we can work with? Well, not really. We see other information about help, but doesn't seem to be our DLL or something that has to do with something we've created. And the reason is that really the functions here, although they exist, they're not really exported. And because they're not exported, the debugger doesn't really know what to do. So we have to export them outside of DLL to be part of the export table. And one way of doing that, which I think is the most convenient here, is to add what's known as a module definition file. So I'm going to look for something like module definition file. We'll find this. We're going to give it the name of the project, like so. So we have this dev file. And what the dev file has is just a bunch of exports. Everything that we're exporting from this function, from this DLL. So we have here two things that we export at this point. One of them is the initialization function. And then the second thing is our help function. So let's go ahead and do that. Okay, let's build it again. You can see it doesn't work. It doesn't work because the DLL is still loaded by the debugger, and so we have to kind of let it go. So let's go ahead and do that. And using the short name is good enough because the debugger is looking in its list and finds that it's just one file that has that kind of name. And so if we build again, it now links back again. Let's try it again. I'm going to do a load to load this again by using the up arrow key to go on to the history of the commands. And now if I do help, let's see, we get our help. So apparently our DLL is properly loaded and it shows its first command. Might be not that interesting. So you might be wondering what happens if we have this help command, but there's obviously many other help commands around. And so technically, if I just use help, the latest DLL being loaded, the latest extension DLL is the one that takes precedence. If I want to look at a help command or any other command that might be duplicated with another DLL, I could provide the full name. So for example, types ext and then .help, that would be the full command for help. So it's always possible to provide the extension name so that you'll be able to distinguish between commands that might have the same name as it happens. Okay, so we have that. Great. Let's go ahead and unload this DLL now. So we'll be able to change it and then do the actual thing that we're interested in, which is writing a command called object types. So here goes. I'm going to export it, but of course the real work is here. It's going to be object types, and we get the same parameters as before. So what do we want to do in the object types command? And so what is going to be our strategy to implement these walking over all the various types? So one option would be things that we've seen here is to maybe go with the object command or something similar to find the object the object types directory in the object manager namespace, and then enumerate whatever is there, and then use those addresses as the basis for getting the object types. This is definitely possible, but pretty hard work. There's an easier way, fortunately. And so as it happens, the list of all the object types are stored in a global variable, which is not exported, but it is available in the symbols, and we can take advantage of the symbols, of course. And this variable is called the OBP object types. So if I do something like this, DQ to show quad word, what we'll see here are addresses of type objects. And so this is just the beginning of the list. Let's verify. I'm going to grab one of those like this one and use the DT command with the object type and paste it in. You can see that indeed this is an object of type user APC reserve. And if I grab something else, we can grab this one and do exactly the same thing and check this out. And so this thing is a process. That's a process object type. So obviously this seems to be working correctly. So we want to go over all these addresses here until we land in something that indicates that we're done, like maybe a 0 or something, 0 address. And that would be easier than trying to parse the various object directory structures, which is definitely something you might want to do for benefit for other commands. But here I'm going to stick with something that is as simple as I can possibly make it. And so we have this symbol that we want to definitely use. I'm going to copy that. And so now we can leverage some of the macros that we get. For example, one of the macros is called getExpression. And this is all, by the way, documented. Of course, I'm not making anything up here. So if we look at things up like getExpression, you notice that, well, that's an example of one of these functions for writing debugger extensions. So you can see we get some value here, but that's not actually the real function. Let me just find it from a different perspective. There's the dprintf function, which we're going to use. It's actually a macro, and that provides, let's locate it. You can see there's various helpers here. These are the functions we get that can help us do things in a easier fashion than going through the direct interfaces, which we always can go through for things that are not perhaps provided by these macros. So one of them is really getExpression, which just returns the value of any expression given some address. So that's what we're supposed to get here. And so for our purposes, what we need is this this global variable, which is OBP object types. So we're going to get its address using the getExpression. This is just interpreting the expression as it would normally do. And so if this is 0, for instance, it means something has failed. And we can say that using the dprintf macro, which is like printf, but writing to the console or the command window of the debugger, that something is wrong, fail to locate that particular value. And that could be, for example, because we don't have any symbols. That's one option. Another option is that someone tries to use this command in user mode debugging, where this symbol is not going to be available even if symbols are properly configured, because there is no kernel module in user mode debugging. And so whatever reason may be, we don't want to move forward unless we can grab the address of this thing. And so now we can finally go ahead, start to provide the actual implementation. So I'm going to go and look at types here. While it's not 0, let's do something, because at the end of the day, at some point we're going to move it forward. Every time we're going to move it to 8 bytes forward in memory, because we can see that it's just the beginning of this list of numbers. So we want to read every number here on the list and then move forward and until we have nothing else to read. And so I'm going to go with a loop while types is not 0. So we need to actually read the actual type itself, the type address. We can use another macro or a function that is provided by the helpers there, called read pointer. It says basically, give me an address, I'll return to you the pointer that is stored in that address. So basically it reads 8 bytes if it's a 64-bit debugging session, or 4 bytes otherwise, and returns that to somewhere. So I'm going to return that to type, to that original type. If this fails for some reason, we'll just break. It shouldn't really fail because the address is valid, but if type is 0, it means that we're done with the list. We're reading 0, which is not a valid address, so we can go ahead and break, which means we're done. So now we can go ahead and read information from the structure. So remember, the structure in question is this object type structure, and we want to read some details like the index, total number of objects, and so on. So to do that, we need to read the actual value. So let's first create variables for them, like something like total objects and total handles, and also create something for peak objects and peak handles. And let's create something for the index. I'm choosing the types as appropriately based on the information we see in the debugger. So in the debugger, these total numbers, we can just, to make it easier to see, we can display the structure without any data. So you can see the total number of objects and handles and the maximum and so on. They're all 4-byte numbers. And index is an unsigned character that is a single byte. So I want to make sure I match up the correct sizes here. And so I have these variables ready to go. There's just need now to actually read them. So one way to do that is calling the function getFieldValue. GetFieldValue is in fact a macro that wraps another function that actually allows to read from the target's memory. So the address is type, that is the address of the current type we're looking at, and then we need to tell the debugger which type we're interested in. So that's object type. It needs to look at a particular field based on that object type, and the field is whatever the field name is. So for example, for index, the field name is index. Why? We see that exactly right here. Technically, we could have defined the object type as a C structure and then read the entire structure in one swoop. This is definitely possible, but this is what I'm doing here is actually safer, because if this structure is changed in some different Windows version, then we'll get an error. On the other hand, when I'm asking the debugger, get me the field index, I don't rely on knowing where the field index is within the structure, because it could be in a different location in some future Windows version. So in this particular example, it's probably not going to change anytime soon, but in general, you want to be careful about that, because you don't know exactly which version of Windows you're working on or looking at. And it's possible that structures change, especially if you're looking at more complex structures like eProcess or eThread. These things tend to change, and members tend to change a position, even if they're not actually removed. So this is going to give us index. You might be you might be thinking something looks fishy here. Maybe I should have an ampersand here to have a location for this to write, but in fact the get field value is a macro, and that macro actually calls another function called get field data, which also allows us to provide the size of the data, and it uses an ampersand here automatically. So in fact, if you put an ampersand, the compiler will not understand what you're doing, so we actually don't want to put an ampersand here. So that would be for the index. Then we need to get the total number of objects. And of course, we have to be very careful to provide the correct names. We can do that, of course, by just copying from the debugger's output for the type. So we have total objects. We also have total handles. So let's grab both of these. And then we have a couple of more for the peak number. They're called, in terms of members, they're called high water. That's short for high watermark. And we can just change it here to peak, like so. So we have that. You might be thinking we're missing something. We are missing the name of the object type, the name of the type, and we'll see how to get it very soon. But for now, just for testing purposes, let's go ahead and display some of that information, see what we get. So let's display the address of the type. Let's display the index. Let's display the number of handles and all that. So let's just use some simple printf kind of style to see what's going on, and try to make it like written in a tabular format in a nice way as much as we can. So we have the type itself, the type address, and then we need to provide the index. So we have the index, and then total objects, total handles, and peak objects and peak handles. Next, we need to move to the next type, which means we need to add to types the size of a pointer to move to the next pointer in line. And while we're at it, let's just count how many types we have. So let's have some variable here like count, and do a count ++ here. And at the end, let's just printf that and say total objects, and just display that information just for fun. Okay, let's try it now. So I've built it, and since I've unloaded it previously, we can build it properly, and then we can load it again. So I'm going to scroll up to find the load this long expression, and then we can use object type. So notice now that object types is also recognized here by the debugger as one of the optional commands. Let's go ahead, see what we get. And indeed, we get what we were hoping for. We can see the object address, so we have the index, and then the number of objects, number of handles, peak number of objects, peak number of handles, all what we ask for, we get that, and it seems to be working just fine. So that's nice. What else? We're missing the name. So let's see if we can add the name, which is slightly trickier. So let's go ahead and unload the extension while we're at it. And so how do we get the name? So as it happens, the name is a Unicode string, and Unicode strings are a bit more complex because they have a pointer, and that points to the characters, and then there's a length and so on. But fortunately, life is pretty good because we have a particular % something which is special for showing Unicode string. That's MSU. To see that, we can go to the dprintf macro here. You can see there's some special stuff which does not normally exist in a printf, in a real printf, such as MSU, which basically says, give me an address of a Unicode string structure, and I will read its information from the address space appropriately based on the length and all that, and display that while I'm at it. It's actually very convenient because otherwise I'll have to do some work to read the Unicode string appropriately before displaying it. So that would be MSU. And to make it slightly nicer in terms of display, I'm going to have 33 characters used for that, so we still contain the tabular way of working. So I'm going to bring, so the thing is that what I need to provide here is the address of the Unicode string. And so if we look at the debugger again, by looking at the object type, we can see that name here is 16 bytes, that is 10 hex bytes after the beginning of the structure. So technically I can do something like type plus 10 hex to provide the actual address where the Unicode string is stored in kernel memory. So now the dprintf with the MSU command can do the right thing. Would that work? I think it would, but it might not be ideal because again I'm using some hard-coded value here which might not be the same on every Windows version. Maybe right now is 10 hex, maybe it could be different in the future, or maybe in some past Windows version. So we'll see how to deal with that momentarily, but let's just first make sure this thing works. So here's loading that, here's object types again, and it works as expected. So it works kind of nice. So we have here the object, that's the object type whose actual name is type, and then directory, symbolic links, and so on, and it seems to be working just fine. You can also add some header to this kind of table. You can just use dprintf in some meaningful way, like a name and then something and so on. I'll leave that as an exercise for you to make it nicer with a proper title. So what about that 10 hex? Can we do something about that? Well, obviously yes, we can do something about that. As part of the information here, there might be something that can help us. Maybe get field offset. That seems to be something that might be useful. So we can get the field offset for a particular type so that we don't have to depend on something that is hard-coded and might not be exactly the same. So let's have a name offset here, and let's call get field offset. And so we need to provide here the type. Of course, the type, we know what that type is. Here goes. And then we need to provide the field itself, which is called name, and we'll get back the offset. Okay, so we expect, of course, this to work. Sorry, need to be an ASCII string, my bad. And now we can use this name offset here instead of something that is hard-coded. Okay, something like this. Okay, let's try it out. So we need to first, of course, we need to unload our extension. So let's unload it. Go back, build, and now load it back, and object types. And it works as expected. So that's probably a safer way to work in general, even though the object type structure probably won't change anytime soon, and in fact hasn't changed in many years. Still, that's a good way to go. You don't want to work with some hard-coded values which depend on some structure which is just the particular one you happen to take a look at. So what else? The last thing I want to do here is something like a nice touch. For example, we know that in the debugger, if I use certain commands like say lm, well, maybe not lm, but I see these links. These are DML links. So these DML links allow us to do various things, to just make it easier to show extra information simply by clicking. And that's obviously something that is nice to have. So how about taking all these addresses and making them linkable, clickable with a DML link, a debugger markup language link, so that anyone can click and get the DT for that particular type object. So let's go ahead and do that. So that's going to be kind of nice. So let's unload first and go back. So how do we do that? Well, apparently the dprintf command here doesn't support that. We have to actually go with the actual interface here. So in this case, I'm going to have to go with the idebug control interface. Control. Let's call that control, and I'm going to query interface from the client. Remember that the client interface is always provided as a parameter to any function that will be able to use it to get the full power of the debugger engine. And then instead of dprintf, I'm going to use control, and there's a controlled output method that we want to use, and it requires a couple of extra parameters like debug out control. Here's where I'm going to specify that I want actually DML. So let's ask for DML interpretation. It's going to be slightly slower, but still, this is what we want. So I'm going to go for that, and it probably won't be really noticeable. So, and then there's another parameter here for type of output, whether it's a warning, an error, or something like that. I'm going to specify normal because it's not really doing anything new. And so once we do that, we get support for DML, but of course we have to do something in order for this DML to actually show up. And there's a simple syntax for DML. There's like an HTML kind of a markup called link, and then we need to provide the command that we want. And so the command that has to be in quotation marks is going to be dt and t with object type. And we need to provide the actual address of the type object. And then we can close the quotation marks here. And then we can specify what we actually want to display, which is exactly this, and then close the link. That's how that is going to look like. That's what it's going to look like, which means that now we need another type here. So if we're trying to match things up, the first thing is the name. So we have the offset to the name. Then we have the %p here for the type to replace that for the link if anyone decides to click. And then we have this actual display, which is another same address, which is actually going to be displayed with a 0x as a prefix, just my decision. And then the rest is as before, the index and so on. All right, let's give it a shot. Okay, let's load the extension and try it again. So obviously, at least we see something. We get the links. Let's click something and it works. We get the command itself and we get information about the object type if anyone chooses to click. So that's an example of writing a WinDbg extension. And you can do all sorts of interesting things to make your life within the debugger easier, which is very important if you want to be more streamlined and spend less time doing repetitive tasks. Then writing custom commands could be one option. It's not the only option. You can also use scripting, and today's debugger supports scripting like with JavaScript. So it's not just the internal scripting engine, the old one, but now the new debugger engine supports JavaScript functions using an object model, which is something I might demonstrate in some future video. If you want to learn more about WinDbg, check out my course, Mastering WinDbg on TrainSec.